Okay, so the next lecture in this unit is about error propagation. So there's a little bit of extra at the end of this lecture about statistical fallacies, but I'll just leave that for you to review on your own. I think the most important thing for this lecture we'll need to know is about error propagation or uncertainty propagation. Excuse me. So we're going to take a look at how to propagate uncertainty using partial derivatives. And that's sort of the only thing we're going to cover. Um, these other topics we might discuss on Tuesday when we discuss experimental design. So just today we're going to focus on partial derivatives for propagating uncertainty. Okay. So let's say that we have a random variable x, and we're computing, this random variable. And let's say we're computing a function of the random variable. You can also view this as more like maybe y is a random variable, and x is maybe an element in the sample space. But anyway, what we want to do is then compute the probability of y. So this is basically like we have a probability of seeing an element in the sample space or a random variable, and we want to compute a function of that random variable. So obviously y is a random variable itself, and so we might want to know about things like what is the probability that y equals 5. Now to make this more practical, let's say that x is something where we measure a compound on a mass balance, and then y is the number of moles. So that is, x is a random variable because when we go and you measure mass, it's a random variable because there's error in, how we prepared our sample. There's error in the balance. There's error in the calibration. So then if we compute the number of moles, right, that's going to be the mass we measured out divided by the molecular weight. In this case, the molecular weight is 18, so it's water. So let's say that we try to approach this problem using some of the statistical techniques we learned. So let's say we're basically measuring water. So we measure out 5 samples of water, and maybe we're trying to make them all the same volume, for example. And then we see, okay, the first time we got 3.5 grams, then 3.4 grams, then 3.3 grams, then 3.6 grams. So I can compute a confidence interval of x, right? I have, 5 samples, so I can compute a confidence interval for x. But then maybe what is the confidence interval for y? Like, we can compute confidence intervals for x, but how does that translate to what the y is? Now, one thing you could do is convert all these measurements into y values and then compute the confidence interval for y. That's possible in this situation. But sometimes we don't actually have the measurements. We only have the confidence interval of x. And an example of this might be like if we did regression and x was a slope and we had a confidence interval for the slope, but then we did a conversion on the slope, then we wanted to know the confidence interval on some conversion of the slope. All right. So that's where we use this technique called error propagation. So the way we do error propagation is we approximate how changes in the random variable x affect changes in the random variable y by using the first derivative. So if you think about it, right, if you're at a point and you look at the first derivative, it tells you the slope of the tangent line. So that tells you how if you move a little bit left or a little bit right, how that will change your independent variable or your dependent variable y. Now, this assumption of approximating, the first derivative with a single point, this is valid when the delta x is small. So that is, if you have a small error or small uncertainty, it's completely valid to evaluate the first derivative and then use that. Okay. So this means that if I have a width in x or an uncertainty in x, I can convert that to an uncertainty in y by multiplying it by the first derivative of my equation evaluated at some point. And that point is supposed to be where you're trying to do your estimation. Okay. So that's the setup. So we're going to try to convert uncertainty or error in x to uncertainty or error in y by just multiplying it by the first derivative evaluated at some point. So let's see an example. So this is me computing the confidence interval. Okay, so that's all I'm doing here. So I take my samples, I get the sample mean and the sample standard deviation. Then I compute a 95% confidence interval using t-statistics. I use t-statistics because I don't know the population standard deviation. So we only have 5 samples. So my degrees of freedom is 4. And I use 0.975 because it's a double-sided confidence interval. And then my width is going to be that t-value times the sample standard deviation divided by the square root of the number of data points. So that means that x is equal to 3.4 plus or minus 0.2. Oh, 0.18, 0.19. I don't know. I guess I wrote this wrong. It should be 0.197, so 0.2 approximately. So we want to find, so we want to get y, what y is equal. So x is equal to 3.4 plus or minus y. So what is y equal to? So our equation, remember, is that y equals x over 18. So then to get the, did I write the derivative? Okay, I didn't write it out. So the derivative of this, right, is going to be 1 over 18, right? So the derivative of this expression is 1 over 18 with respect to x. So dy dx is 1 over 18. Then I multiply the 1 over 18 times my width of x, or my uncertainty in x. So it's 1 over 18 times the confidence interval width of x, and that will give me the confidence interval width of y. So the number of moles is going to be 0.19 plus or minus 0.01. Okay. Now, it's a coincidence that these equations are the same. It's not correct to just, like, I understand in this example, you could just plug in wx here and you would get the same answer, but that's not how it works. It's a coincidence that in this case, for linear equations, if you have it just where y is proportional to x directly, it's a coincidence that you can just plug the interval width into the equation. We'll see other examples, like where we have a 1 over x, where we have an x squared, where it's not the case that converting the confidence interval width is the same thing as just plugging it into the equation for y. So this one is just a coincidence that these two equations are the same. That's not always the case. Are there any questions so far about how to do the error propagation?
What if you don't have like a function or like data that doesn't fit a function?
What if you have data that doesn't fit a function? I don't quite follow. Could you explain that a little bit more?
Yeah, so like what if you have like discrete data or something, like you measured something from for x, but you don't have quite the information to obtain a function to obtain this derivative?
I understand what you're saying. Right. So, okay, so the question is like, what if you don't have an analytical equation like the f of x? So error propagation, like what we're doing here, that is propagating uncertainty through functions. So this analysis we're doing tells you how to have uncertainty in one variable and go to uncertainty in another variable. So it always assumes like the only way we can do error propagation is if we have functions. So this is basically how do you deal with uncertainty going through functions? Like that's what we're describing here. So if you don't have functions, then there's no error propagation to be done because you're not propagating the error through anything. Does that answer your question?
Yes, thank you.
Yeah. Okay. So let's see an example where the first derivative is not coincidentally the same as the original function. So let's say that we're measuring volume of a sample with known mass. So now mass is known and we're measuring volume. Okay. And we obtain different volumes. So 1.2 mils, 0.9 mils, 1.3 mils, 1 mil, 1.3 mils, right? So each of these samples has the same mass and we're measuring the volume. So the mass is 1 gram and it's known. So what is the density and what is the uncertainty in the density? So the equation for density is going to be the mass, which we said is 1 gram, divided by the volume, right? Because density is in mass per volume. So if we compute the derivative of this expression, it's minus 1 over v squared. So then the uncertainty and density is going to be minus 1 over v squared times the uncertainty in volume. Okay, so this one is very different, right? So it has a minus sign, and it's a 1 over v squared times the uncertainty in volume. So here, the density is actually going to be pretty sensitive, right? We have a v squared term, so this is going to be maybe, oh, sorry, maybe not that sensitive. It depends on if v is less than 1 or greater than 1. Okay. So again, I compute my confidence interval of the volume using the values that were given. And we find out that our volume is 1.14 plus or minus 0.22. Then to get the uncertainty and the density, I take minus 1 over the mean squared. So I have to plug in my estimate for the volume, and I use my v hat, right? So I have to put in a number to evaluate this first derivative. So I use my sample mean. And then I multiply that by the confidence interval width. So my density is 0.88 plus or minus 0.17. Now notice the minus sign has no effect, right? Because it's plus or minus, and now it's minus or plus, I guess. So the minus sign actually doesn't make any difference for the confidence interval width. It just means that if your volume were to be a little bit high, then your density would be a little bit low. Or if your volume were a little bit low, your density would be a little bit high. It just tells you that sort of these things move in opposite directions. But as far as if you have a symmetric confidence interval, like if your confidence interval is plus or minus, then the minus sign doesn't make a difference when doing the error propagation. So this is an example of how, when you take these partial derivatives, it isn't just the same thing as plugging into the equation. It is a little bit more complicated than that. Okay, are there any questions on this example? Okay. So the next question is, how do you deal with multiple dimensions? So the way we do multiple dimensions, this equation is kind of intimidating, but it's actually pretty straightforward. So all you do is you evaluate the partial derivatives of each independent variable which has uncertainty. You evaluate its partials, multiply them by the uncertainties, and then you take sort of the Euclidean norm. You square everything, add them together, then take the square root. Okay? So this equation looks pretty scary, but it's pretty straightforward. It's basically you evaluate, sort of the first derivative times the uncertainty for each of the things that have uncertainty. Then you square them, add them up together, and take the square root. So in 2 dimensions, it would look like this. You would take the first derivative with respect to x, and then multiply by the uncertainty in x, and then square that. Then take the first derivative with respect to y, then multiply by the uncertainty in y, square that. And then you add those two together, and then take the square root. And that would give you the uncertainty in the function. So we're kind of working towards an example here. And so let's say we were trying to compute density. And now we're measuring volume and mass. And so these are the 2 examples we did before, but now they're combined. So we have multiple mass measurements and multiple volume measurements, and we're trying to estimate the density. So the question is, what is the 95% confidence interval for density? So here are our values. So the partial derivative. So the partial derivative of density with respect to mass is going to be 1 over volume. Then the partial derivative of density with respect to volume is going to be minus m over volume, mass over volume squared. So here I compute my 2 confidence interval widths. So here's my mass confidence interval width, and here's my volume confidence interval width. So this is like what we had done before. So these are the 2 confidence interval widths. Now I did something kind of, I mentioned at the beginning that we want to make sure to do this kind of analysis, we have to make sure that the delta x, that the uncertainty of each independent variable are small. And when we say are they small, it means they need to be small relative to the partial derivatives. Okay, so at the beginning of this, we had said that the delta x needs to be small. So you can check that relative to the partial derivative. So that's all I'm checking here. Basically, here's the partial derivative of mass, here's the partial derivative of volume. And notice that the confidence interval width and the volume interval width are much smaller than these. right? So when is the assumption bad? It's when this confidence interval width starts becoming much larger than the partial derivatives. In practice, almost everyone in engineering ignores this. No one pays attention to this. So I mean, I'm not going to test you guys on this, but just something to keep in mind is that this error propagation thing is an approximation, and that approximation breaks down when you start getting to large uncertainties with respect to the first derivatives. Okay. Then to put it all together, we have the value of the first derivative squared times the confidence interval width squared for mass. Then for the volume, we have the value of the partial derivative of volume squared times the confidence interval width volume squared. Then we add them together and take the square root, and that gives us our uncertainty and density. So our final density is 2.98. I guess you could say 3 plus or minus 0.6. Okay, so that is a complete example for getting the uncertainty through error propagation. I think that covers that. So are there any questions on error propagation? So one thing we haven't really discussed is that in engineering, a lot of times we'll be using instrumentation, like a mass balance or pressure meter, and there will be a known uncertainty from that instrument. So that's called instrumentation error, instrumentation uncertainty. So like you might have a pressure meter and it's known that it has, a 1 psi certainty or 1 psi uncertainty, I should say. So then if you wanted to say, if you use that pressure meter to then compute flow rate, you can use error propagation to show what is your uncertainty in your flow rate due to there being uncertainty in your pressure gauge. So a lot of times in your junior and senior level classes, in your lab especially, people will say, do your error propagation or do error propagation analysis. And what that means is that if you're going to compute numbers like flow rates or you're going to compute, say, reaction rates, you need to take into account any uncertainty in instrumentation or any uncertainty in your experimental setup that you can establish from doing confidence intervals and propagate that through to your final numbers. And so in this class, we've learned two ways to do error propagation. So the first is if we have uncertainty in our data and we're doing regression. We saw in Unit 12, Lecture 3, how to do regression with uncertainty. And then here in this lecture, we see how to do uncertainty propagation when we're doing just analytical equations. All right, so are there any questions on this? All right, if not, that concludes the lecture for today.